And welcome back to Mr. Gregoris Math. So earlier we were taking a look at geometric series, and I alluded to the words of Buzz Lightyear, who of course famously said, "To infinity and beyond." And I know Disney's probably gonna charge me or whatever if this video monetizes. And to the people at Disney, I'll say, good luck drawing blood from the stone. So hopefully that doesn't trigger any YouTube examining, I don't know, probably not. Regardless, we're going to take a look at a special type of geometric series. So this geometric series is going to be something that we're going to call convergent. So a convergent geometric series would look like this. So it'd be something like, let's go with like 3 plus 3/2 plus 3/4 plus 3/8 plus 3/16, and so on and so on and so forth. And so what you can see is each value is getting pretty large. So here's 3. Each value is actually getting subsequently smaller. So the next value is 3/2. So it would only go to like there, because you'd have those like 3/2 that make it up. So it'd be exactly half the height. And then the next value after that would be 3/4. And so that would be like half of 3/2, because each half would be split into quarters. And so you'd have your 3/4. And I can imagine picking this piece up and just going ahead and putting it right here. So there should be a quarter up right here. There's 1/4, 2/4, 3/4. And I'll change colors so we can see where I'm going to do 3/8. So 3/8 would cover, again, there's 1/4 left here, so that'll be a little bit more than that 1/4, so that's 2/8. So there's your 3/8. And eventually 3/16, that's going to be pretty small too, and so we'll work our way down. And we'll get 3/16, this is going to be right about there. 1, 2, and it's getting to the point where it's too thin for my marker to actually fit in. But what we can probably see here is you can probably see that eventually, this is going to keep growing and growing and growing, and it'll probably fill in that secondary gap there. So it'll probably fill in this whole thing. So we would say we have, okay, well, there's 1 from here, 2 from here, 3 from here, and this is the same width, so that's 4, 5, and 6. We might say this sum, as it continues on to infinity, might look like it's going to work out to be 6. And in fact, that is what it works out to be. It does fill up that other bit of space. So let's see how that happens. So the first thing to recognize is this is just our general term, U1. And then to find our R value, we find the number we multiply by to get from here to here. And so our R value in this case is equal to 1/2. Because to get from 3 to 3/2, we'll multiply by 1/2. So you can see that pattern continues. 3/2 times 1/2 is 3/4, and 3/4 times 1/2 is 3/8. And so it is in fact R is 1/2. And that's very important, because if the absolute value of R is less than 1, we can conclude that our series, or our geometric series, is convergent. So this implies we have something that is convergent. Now, there is convergent and alternating, and there is conditionally convergent as well too. But we're going to stick with things that are absolutely convergent, like this one. This one is absolutely convergent. And so let's go ahead and take a look at what this looks like when we apply it to our formula for the sum of a geometric series. So from that last video, we determined that formula was Sn equals U1 R to the power n minus 1 over R minus 1. Now, n, of course, because it's going to infinity, is going to be infinity. So this is S infinity is equal to U1 R infinity minus 1 over R minus 1. Now, when I think of R infinity, I kind of want to think about that a little bit more closely. I think I'm going to just examine it with a different type of notation. So this would be a little aside. Here's R to some exponent n. And let's actually replace R with our R from our problem. So our R from our problem is 1/2. So this is 1/2 to some power n. So for example, if n is 1, then we would have 1/2 to the power 1, and that would be equal to 1/2. And if n was, really blue marker. If n was 2, we'd have 1/2 to the power 2, and we'd have n as 1/4. And then if n was 3, we'd see that we would have 1/8. And you can see that our denominator is increasing, and our numerator is remaining as a 1. And so what happens if we allow n to go to infinity? So that's what this statement of notation does. It says, what is the limit of this expression if we let this letter n go to infinity? So that arrow is go to, and this is the infinity symbol. So what's the limit of 1/2 to the power n as n approaches infinity? So that's kind of like talking about what happens when we get all the way down to here. Well, what's 1 to the power n? Well, that's 1, and in fact 1 to any power is going to be 1. So really, this limit can be broken apart into 1 over 2 to the power n. Now, infinity is a very large number, so a very, very large number here is going to create a denominator of a really, really, really big number, like 2 to the power infinity is going to be incredibly large. And so we'd be dealing with something like 1 over a really large number. And so a really large number, and by the way, this isn't exactly equal, this is just kind of like approximately equal or informally equal, but this would be 1 over a really, really, really large number. Now, anytime I divide something by a lot of pieces, each piece is very, very, very small. So if I take a number like this and divide it by the biggest possible number I can think of, I'm going to create a number that's going to approach 0, much like we think about approaching asymptotes. So this is going to get to something like 0. Well, let's take a look at what this implies for this expression up here. So if we say as n gets to infinity, this 1 over 2 gets to 0, then when we go back and substitute and we talk about our infinite sum, which I'll now write like this. So it's the sum from n equals 1 to infinity of, now my generalized term would be 3 times 1/2 to the power n. Well, this is u1, which is 3, my r, which is 1/2, is power n minus 1, all over 1/2 minus 1. And we've decided that as we continue going up and up and up and up and up, this expression here is going to go to 0. So we'd say it tends to 0. Or it tends toward, or it moves towards 0. So this is going to work out to be, well, 3 times 0 minus 1 over 1/2 minus 1, which is just negative 1/2. And so we can see this is going to be 3 times negative 1, which is negative 3, divided by negative 1/2. And when we divide fractions, we invert and multiply, so it'll be negative 3 times negative 2 over 1, which is how we got to 6, exactly what we were expecting to see. So this is kind of a cool result here that happens because this term that goes to infinity tends towards 0. It's important when we're talking about convergent things, because that term toward infinity is talking about the difference between each subsequent square and adding literally nothing else. So because it converges, it's like we're adding nothing else as we get to the last digit of this particular series. So that's a pretty cool example. And what we can do is we can generalize more formally what happens. Because this expression here goes to 0, we can actually do a little bit of a change. So because that goes to 0, I can write this as negative u1 over r minus 1. And that's my sum to infinity. Because that term is 0, and I can just distribute u1 times negative 1. And I don't really like the negative, so I'm going to factor a negative out of the denominator. I'll write it as negative u1 over negative, and I'll write this as 1 minus r. And you can see these two negatives are going to cancel. This is going to leave me with my infinite sum formula. So this formula is valid anytime the absolute value of r is less than 1. Essentially, to find an infinite sum, you take the first term and you divide it by the difference between 1 and the r value. So that's the reason why our r value needs to be less than 1. The absolute value of our r value needs to be less than 1. That's the development of, I believe the formula is called 1.8 or something in your data booklet. But it is really what happens when we let geometric sequences, in the words of Buzz Lightyear, go to infinity and beyond. Don't forget to click like, subscribe, ring that notification bell so you see when we drop new videos. And I'll see you next time on Mr. Gregor's Math. Take care.